Hello and welcome. Here we are today in our class, and we have a special guest lecture. So Kevin from UC Berkeley will be telling us about the new verification features available in Chisel. So this is really exciting. So far in this course, you've watched me hack together various testers to kind of prod individual concrete values. Sometimes really just kind of a demo and not very rigorous testing. And Kevin's going to show us how now with the language and hopefully not too much extra code, we can get much more rigorous testing. So welcome, Kevin. Please take it away.
Okay, cool. Thank you very much for the introduction. So yeah, as Scott said, my name is Kevin Laeufer. I am a PhD student at Berkeley, and I somehow recently became the maintainer of the Chisel test library that you have all been using probably when you write your unit tests. Just a note, if you want to follow along at home, make sure that you have the Z-free SMT solver installed, because our scripts are going to call out to that. You can probably find that SMT solver in your favorite package manager. Okay, so the plan for today is that I'll first talk about the Boolean satisfiability problem. That's like a lot. I don't expect anyone to know about it yet, but we'll go into some details there. Then I'll talk about how can we verify combinatorial circuits, so circuits that do not have any registers or memory. And how can we then we'll go on to verifying sequential circuits that actually do have some state. And then I have some examples that are hopefully applied and like fun enough that they'll motivate you to try out this technique yourself. Okay, so this is the standard loading the library into our notebook. You've seen that 1,000 times. I hope it actually works today. We'll see. And then this is my boilerplate for today. You don't have to understand it. You can look at it at home if you want to, but it's basically just importing some of these helper functions that we'll be using in this presentation. Okay, so first thing I want to talk about is Boolean satisfiability. So what's Boolean satisfiability? It is basically a problem that if you have a Boolean formula, we'll call it F here, and it has a bunch of like parameters or arguments, and all those arguments are Boolean variables, so they can either be true or false or 1 or 0, depending on how you want to look at it. And then the question is, can this function ever evaluate to true? Another way of asking this question is, does there exist an assignment to the variables such that f evaluates to true? So can we set these x variables that go into f, can we set them to true or false in such a way that f will evaluate to true? And in that case, if that is true, then we'll say the formula is satisfiable. We can choose the inputs in such a way that the formula evaluates to true. Another way of asking our satisfiability question is to say, does f for all possible assignments to x1 to xn evaluate to false? So that's the exact negation of the thing we asked before. So if we say that no matter what you assign to these variables, f will always be false, then we say that f is unsatisfiable. Now, in this demo, we'll have this solve function, which is like a magical function here, which will determine for us whether a certain formula that we give it is satisfiable or not. And if it's satisfiable, it will actually give us an assignment to the variables. And if it's not satisfiable, we'll say, oh, it's unsat. Okay. So the first example here is B0 and not B0. So B0 is just a Boolean variable. And so now the question is like, is this formula satisfiable or not? So since we only have a single variable that's the input, we can sort of just brute force it, right? We can just say like, okay, if B0 is 1, then we have 1 and not 1. So 1 and 0, and that will be 0. So that would be false. The formula would be false. If we set B0 to 0, then we would have 0 and not 0, so 0 and 1, and that would be also false. So we know that there's no assignment to B0 that will make this formula true, so it's unsatisfiable. So let's see if the code tells us the same thing. If we execute it, yeah, it says, oh, this is unsatisfiable. Now, I have some more examples here. So like this is like using two variables now. So it says like B0 and B1, right? And we kind of know the truth table for an AND gate. And we know that the only way to make the output true is if we set both inputs to true. And so we'll see if the solver will figure that out for us. Yeah, it says, okay, it is satisfiable. If you set both variables to 1, then the output will be 1. For an OR gate, we know there will be several different ways that we could assign B0 and B1 for the output to be 1. The solver, now that it has like these 3 possibilities, it will just pick 1. It doesn't matter which one for this problem. It will just give you one example that shows, oh, you can make this formula be true. And so here we see it chooses B0 is 1 and B1 is 0. So we see like 1 or 0, that will always be 1. And so that way the formula is satisfiable. Now, let's think a little bit about like how do we actually approach this problem. So as I said before, you can solve this in theory like with a truth table. So you can just like write down your variables and the function output. And so that for every possible assignment to your variables, you just write down what the function evaluates to. And so if we want to see if something is unsatisfiable, we just check the rightmost column and see if they're all zeros. That means there's no way to satisfy the formula. If there's a 1, then we know, oh, this is a way that we can satisfy the formula. So then we can just take the assignments to the inputs, and then we have a satisfying assignment for the formula. So that sounds pretty easy, right? So like, why is this special? Like we can just always like write the truth table and we can always like figure things out. Well, the problem is this truth table, it grows exponentially in size with the number of variables that you have, right? So basically, the number of rows is 2 to the number of variables. So for a 1 input variable, 2 to the 1 is 2. 2 to the 2 is 4. But then if we get like 1 more input variable, we have 8 rows. 1 more input variable, we have 16 rows, and so on. So this was going to like grow exponentially in size. And so if we have a circuit that has like a 32-bit input, then 32 bits is 32 different Boolean variables, and suddenly we have a truth table that's 2 to the 32 in size. And so that means that making a truth table is not really a scalable solution to solving this problem. So this problem is also known, like the Boolean satisfiability problem is known as the first NP-complete problem. What that basically means is in the worst case, like asymptotically, you get a terrible runtime. So basically in CS, we sometimes think about these problems as sort of these impossible problems, right? Like you cannot solve them because they're NP-complete. But in like the 1990s or early 2000s, researchers were actually like, okay, we know that there's always some cases for which it will take us exponential amounts of time to solve this problem. But it turns out that in a lot of like cases that we're interested in, like real life cases, this problem can actually be solved pretty quickly. And so how does this not like invalidate the theory? Well, the theory only talks about sort of the worst case. It says that you can always construct a problem where it takes an exponential time to solve, but it doesn't necessarily talk about the general case. And so for this problem, there's a lot of like heuristics. So like basically algorithms that work on a subset of these problems that can be very quick and can like solve these problems for you. And so nowadays, a lot of formal verification or also other applications sort of use this, use sort of a solver, which we call a SAT solver, that can quickly solve this Boolean satisfiability problem for a lot of real world applications. But of course, not in the general case, because that's impossible. The next thing I want to talk about is SMT, stands for SAT modular theories. You don't have to really understand a lot about it. The most important part here is that so far we've only been working with Boolean variables. So like either variables that are either true or false. And SMT basically just adds some richer data types to what we've been doing. So a bit vector is basically a fixed bit with integer, and that's something that we will see if we have a C program. So if we have like an int in C, it could be 32 bits, for example, and then you have like some overflow things, and there's like some special behavior because it's like the integer is actually finite and it's not like a natural number. And also like in our circuits in Chisel, right, you can have a uint that is basically a bit vector of a certain size. And so let's have some fun with this, with these uints. So A is the variable that I defined earlier. It's basically just a 32-bit variable. And so we say, okay, we want to solve this formula. We want to see if there is an assignment to A such that A plus A is equal to 8. And now you can all think about sort of like, what's the solution here? Think back to your elementary math classes. Is basically 2 times A is equal to 8, right? And so the solution that we expect here is 4. Yeah, so we get 4. It's just like, oh yeah, if you assign A to 4, then 4 plus 4 is equal to 8. Now the question is, can we do the same thing where we say A plus A is equal to 9? So think about this a little bit and like sort of like maybe like make a decision in your head whether you think it should be satisfiable or unsatisfiable. And now I'm going to execute it and we'll see it is unsatisfiable. Why is it unsatisfiable? Because, well, you would have to be able to reason in fractions to like give an answer to this, right? Like the solution would be like 4.5 or 4.5. And since these are integers, you can't actually represent that. So an integer times 2 is equal to 9. You don't have an integer solution to that. And so that's why it comes back and says it's unsatisfiable. Now, another thing you want to do here is this kind of fun trick that we sometimes do for compilers. It's kind of like strength reduction. So basically, we have some value that's multiplied with a constant 4, and we want to replace this with a shift by another constant. And now we're basically asking the solver to find a constant for us for which this identity holds. And so we'll say, okay, try to find this. And what it will return is it will say, okay, if a is 2, that means that this like c times 4 is equal to c shifted by 2. So we can also like change that, right? We can say like, oh, we want to do times 8. So let's do times 8. And then what would be the result? It would be 3, right? So here we get a 3. Another question is like, oh, can we do this if something is not a power of 2, right? Like c times 5. Like, can we just find some way of shifting it? And so we can try to create a solver. And you probably guessed it, like the answer is it's unsatisfiable. Like you can't find an assignment for a that will make this formula be true. So this is SMT. There's also arrays, which I don't have a demo for, but basically it's just a way of modeling that you can store and retrieve things from a memory. So this is important for a C program, right, where you might have an array that you access. It's also important for hardware. So if you think about your queue implementation, it's using a memory, and we kind of want to model that if you save something to a certain location in memory and then read from that location, you will get the last value that was saved at that location. So that's basically what that part is modeling and what it can reason about. So yeah, that's just like sort of the basic technology that's behind this formal verification approach that we're going to discuss today. So now let's get to our first more real circuit example. So we want to verify a combinatorial circuit. What does it mean for a circuit to be combinatorial? Well, it means that we have no state elements, basically. There's no registers and no memories. And the nice thing about these circuits is that we can, if we have an assertion in those, we can directly map it to an SMT formula. So let's look at this little like circuit sketch here. It basically has an A, which is an input that's 32-bit wide, and we have B, and B is just equal to A plus 1. And then we have an assertion. So an assertion basically just specifies a value that should always be true. And if you find a way to make that assertion, the value inside the assertion be false, then you found a bug. That's sort of the idea behind this assert statement. And now here we're asserting that, oh, because B is just A plus 1, B should always be greater than A. Right, so that's like the thing that we're trying to prove here. And so now we have to encode this somehow. And how do we encode it? Well, we make a big like conjunction, like a big and we say, okay, first of all, we say B is equal to A plus 1. So we're just defining this fact here. We say B is equal to A plus 1. And then we're saying, okay, does there exist an assignment to A and B such that the assertion does not hold? So we're basically asking the negation of the assertion because we want to get an example for when the assertion fails. And so if there's no example, no assignment to A that makes the assertion fail, then we have proven the assertion. So here we're saying not greater than BA, which is just a negation of the assertion. And so we'll check that. And you can think about it, should this hold or not? And it turns out it doesn't hold, right? So like there's like this assignment to A, this like big number. And apparently in that case, B is 0. So why is that happening? Well, we can visualize it a little bit. Think about the fact that like A is a 32-bit value and how like addition works in Chisel. So here, basically, we can see that A is basically just a bunch of ones. And if you were to count them, it would be exactly 32 ones. And so now, because addition in Chisel doesn't actually add another bit to your result, it actually, like if you add two 32-bit values, the result will be 32 bits. That means that in this case, basically, if we add 1, the carry will be here at the bit 33, but bit 33 is always cut off. So then the result will be 0. And of course, 0 is not larger than all bits set to 1. And so that's why there is a counterexample actually to our assertion. And that's like an important difference between like a bit vector, like a limited precision integer versus an actual, like mathematical integer. Okay. So this is just to show you that you can now do this also in Chisel very easily. So basically from the Chisel test library, we have this new verify function, which is very similar to the test function. You just give it your design that you're trying to test. And then you also have to give it a series of commands, or at least one command. Here it's called a bounded check, and we will get into the details of what exactly a bounded check is later. But right now, just trust me that if you only have a combinatorial circuit, you can set bounded check to 1, and it will basically either prove that it's always correct, or it will produce a counterexample. So here we can run this and see what happens. It's all a little slower today, I think, because of Zoom. Okay, here we go. It will say, oh, the assertion failed. And here in this case, because we have this little print thing in the assert, we actually will get a display of what's happening. So it says A is this and B is this, and obviously this is larger than this. Okay, so this is where you can get the exact same answer with Chisel. Okay, now I just wanted to show you some applications. So this is an application that I recently actually used. I added something new to the Chisel library, and I wanted to verify that it is correct. And the thing that I added is a Graycode conversion. So I'm not sure if anyone here is familiar with Graycode, but basically Graycode is an encoding for binary numbers that is very useful if you want to cross different clock domains. So if you want to basically have your memory system run at a certain frequency, and then your core run at a certain frequency, you want to cross some information between these clocks, these circuits that are connected to different clocks. And so one thing that the physical designers want to see is that if you have a counter, only one bit should change every time you count up. But that's not true for binary. So if you think about 3 in binary, it's 1, 1. And if you add 1, you get 4, and 4 is 1, 0, 0. So going from 3 to 4, 3 bits toggle, and that's bad if you're crossing clock domains. I can't actually explain to you exactly why it's bad. I don't know enough about the backend story, but that's basically something that the physical designer will tell you. You need only 1 bit to flip, and so that's why we have Graycode. And Graycode basically has 2 important properties. One of them is we can convert it back into binary. So we can go from binary to Graycode to binary, and we don't lose any information. And so this is what this is checking for. So here we're saying there's an input of a certain width, and we convert it to Graycode, and then we convert the Graycode back to binary. And we're just checking that for all possible inputs, the input will always be equal to the output. So we can run this, and you're seeing here, we're checking it actually for 64 bits wide, for a 64-bit wide input. And that shows you how this technique is more powerful than just exhaustive testing, because if you wanted to do exhaustive testing, there are 2 to the 64 different values that you can assign to in, and that would just take a really, really long time, right? And so you see that the solver is doing more than just brute forcing your solution. It's trying to find some structure and then sort of prove that this is correct. Now we can't see anything because the assertion is always correct, but if I just mess with the assertion, right, then it will actually produce a counterexample, which is not a real counterexample because I actually changed the assertion. But here we can see basically, if you have 0, the Graycode will be 0, and then the output will be 0. So this is just an example that the solver comes up with. And this looks like it actually fulfills our property, right? The input is equal to the output. What's the other property? Well, the important property that I talked about earlier is that when the input is incremented, the binary input is incremented, the Graycode only changes by 1 bit. So how can we express that? So we make another module, also parameterized by a width. We again, have some random A, some arbitrary value A. And then we say, okay, we have B, which is just A incremented by 1. And now we convert both of them to Graycode. So we have the Graycode of A, and we have the Graycode of A incremented by 1. And now we want to basically check how many bits are different between them. How many bits did flip? And so one trick, and you might have to just do this once on paper to see why it works. But basically, if you have an XOR between two binary values, only the bits that are different will be set to 1. So if I have I don't know, 1, 0, 0, I guess I should probably write this down. If you have 1, 0, 0 and 1, 1, 0, then the XOR between the two will be 0, 1, 0, right? So only this 1 bit flipped. So what we're doing here is we're basically saying like, okay, which bits flipped, and then we do a pop count, which will just tell us how many bits are set to 1 in this value. And so basically that is the Hamming distance. So the Hamming distance is basically how many bits do you have to flip to go from A gray to B gray. And we want the Hamming distance to always be 1. And we're checking that again for like any possible input value of 64-bit width. And we'll see that like pretty quickly it comes back and there's no error, which means that everything is going well. And so this is like a real example of sort of how you can use this combinatorial circuit verification. The nice part here is that because the circuit is combinatorial, like this binary to gray doesn't use any registers. That means that this property actually holds for, we basically proven this property. And you'll see that for if you have state, actually proving the property is much harder in a bit. So yeah, next we're going to go to sequential circuits. And before that, I just wanted to ask if there was any questions right now. Okay, no questions so far, so I'll continue. So now this is like my summary slide for combinatorial circuit verification. So the important parts to take away from this chapter is basically that you will always have to write an assertion to define the property that we want to check. So a lot of people will tell you like, oh, I've formally verified this circuit or something like that. But that is not actually like a meaningful statement. The meaningful statement is like, what property did you check about the circuit, right? So for the Graycode conversion, we basically had 2 properties that we identified and that we checked. But it could be that there's another property that's important that we just forgot about. And so there could be a bug still that like sort of violates this property, right? So you always have to define sort of what are you actually checking. We learned about SMT solvers and how they can prove for all possible inputs that the assertion cannot be violated. And with the Chisel interface, if we have a combinatorial circuit, we just do bounded check 1 and we'll get a full proof. Those are sort of the main points here to take away. Now let's look at sequential circuits. So this is a simple counter circuit. So it has 1 register basically, and this makes it a sequential circuit. So now let's look at what we're doing here. So we have a counter, it has an enable pin, and it has like this count register. And so now what we're doing is we're saying, okay, when the counter is enabled and the count is equal to 22, then we'll reset it to 0. If it's enabled and the count is not equal to 22, then we'll just increment the counter. So that's like a little bit of an awkward way to write a counter, but let's just like accept it. And now our assertion is like, oh, we don't want the counter ever to be 10. So, and here we have a print statement to just print the internal state. So we'll see if we do a bounded check here. Well, let's first like maybe actually reduce this a little bit. Let's say, oh, we just want to check for like 6 cycles. Then it will actually say, oh, everything is great. But then if we increase it to 10 cycles, it will actually tell us like, oh, I found a way to violate it. So you see this enable pin, that's like free for the solver to choose. Whatever it likes to do, just like the A that we had before. And so here we'll say, okay, enable has to always be 1 so that we can, as quickly as possible, get to the state where the counter is 10, and then it will all fail. We could like change the assertion. We could say, oh, it's never 500. And then in this case, it will pass, but will it actually pass forever, right? Like how large do I have to make this to like know that I can be confident? And we'll talk about this a little later, like how to choose this value. But I just wanted to bring this up for now that like basically the larger you make this, the longer it takes to check, but the higher maybe your confidence. So we'll see. Now, this is just like the motivating example. Now we're gonna like dive a little bit more into sort of the theory of like, how can we actually check this? So if we think about this counter, we can say, okay, this is, we basically want to make a little bit of an abstraction. We don't want to think about a complete circuit. We just sort of want to just think about sort of like, we want to have like a more abstract way of thinking about it. And so normally what we call this more abstract system is we call it a transition system. And that just means we say that there's a state, an initial state, and then it goes to the next state, and the next state. And then the question is there some way to get to an error state? So, so how do we define these? So this is just like an example. So every state is basically like the count and the input. We can mostly forget about the input because the input can be freely chosen every state, and it doesn't actually like come up in an assertion, but you can model the input also as a state. And so we're saying like, okay, the count is 0, then the count is 0, then the count is 1, but that would be like an example, like evolution of the state. And the error state basically just says like, oh, the count is equal to 10, the enable doesn't matter. So like if we can somehow get to a state where the count is equal to 10, then we have found an error. And so basically all it comes down to is like, can we reach this error state? So this is like the reachability problem. Can we go to a state where we have this error? So now here I have like some Scala code that will help us sort of define the system. So we say, okay, there's a state, and we basically just have a symbol for the counter and a symbol for the enable. So basically this make state function will just create a symbol that's called counter 0 or counter 1, no, depending like which state you're in. And then we have make a symbol called enable 0, enable 1, whatever. And now we define some of the properties. We define whether the state is the initial state. So we say the state is the initial state if the counter is equal to 0, right? So the counter is equal to 0. That's like our definition of the initial state. Because if we go back, oops, I gotta get out of here. Yeah, if we go back, then we see like our register, our count is reset to 0. So we say, okay, when the counter is 0, that's our initial state. And then here, this is sort of making the next state. This is a little more complicated, but like, so the ITE basically means a mux. So it means that if the first thing is true, then we pick the second argument. If otherwise, we pick the third argument. So here we're saying if in the previous state, so here this is sort of like saying like S0 is one state and then S1 should be the next state. So if in the current state, the enable is true, then we will check whether the counter is equal to 22. And if it's equal to 22, we'll set it to 0. Otherwise, we'll just add 1 to the counter. And if enable is false, then we'll just retain the old counter value. So that's basically the behavior of how the counter evolves. And so what we're saying here then is we're saying, okay, if S1 is the next state, then that means that the counter of S1 has to abide by this evolution function for our counter. So we're saying like the next counter is equal to this expression. And now here we're encoding the property. So P is sort of the property that we're trying to prove. And the property is that the counter is not equal to 10. And now here we're just making like 2 states so that we can play around with them in the next slide. Okay, cool. So now I guess like 2 questions that we should ask each other about this transition system is like, what happened to our clock and what happened to our reset? So if you go back to Chisel, so Chisel doesn't actually like show you the clock, but we know that implicitly there will be a clock that goes into the counter and that will actually advance this register. But if we look at our like formulation here, we don't actually have a clock. And so what we did basically is we said, okay, the circuit is fully synchronous. Everything like changes on the same clock. And so we can just remove the clock and just say if 1 clock tick is 1 step in this system. And so this is a very easy conversion that you can do if you have a single clock. If you have more than 1 clock, or if you have some asynchronous signals, then the modeling gets more complicated. And that's basically all I want to say about this. It gets complicated, and I could like do a lecture only on like how you model multiple clocks. The other thing is like what happened to the reset. So we were cheating here a little bit. We basically said the counter actually starts at 0, and so we don't have any reset input anymore. The actual like Chisel will have a reset input. So the counter here will actually start at an undefined value, because you know when you manufacture a circuit, you don't actually know what value the registers will be in when the circuit powers up. And then you have the reset signal that will then like make sure that this counter is reset to 0. And so you could model that as a separate signal. That's actually what happens when you like use the Chisel built-in verify function. But for our goal here, we just said, okay, we just know about the reset logic and we know that it will start at count 0. So we basically ignore everything before the reset is released. That's like a simplification we made here. So now what we want to do is we want to do bounded model checking. And what that means is we will start at an initial state. And then we will go like a couple of states, and then we'll say, oh, in the last state, is there any way that the assertion could be violated? So the way that we encode this is we have these symbolic states, like denoted here as S. And then we have these formulas that we defined before. So these are basically what we call predicates. So they're like a formula on the state that returns true or false. And so I basically returns true if it's the initial state. T is defined over 2 states and will return 2 if those states are successive states, if one state transitions to the other. And P will return true if the assertion holds. So the way we can like sort of express this with some math is we can say, okay, S0 should be the initial state, and S0 and S1 follows to S0. And then we like basically have a bunch of different other states up to SK. And then we say, is there any state in which like any of the assertions can be violated? And so that's how you can basically check up to a bound K, whether within K cycles you can hit an error state. So here's our manual example. The first thing we do is we basically just say, okay, assuming S0 is the initial state, is there a way that the property can be violated? And we'll know that the answer here is false, right? Because what is going on here, so it's unset, because what's going on here is we know that in the initial state S0 is equal to, the counter is equal to 0, and the assertion says the counter should not be equal to 10. So that's true always in the initial state. So that's not a problem. Now we can check the next state by saying, okay, let's say we started the initial state again, we transition from S0 to S1, and then we check, can the assertion be violated in S1? And it cannot be, right? Because if you think about it, there's only two possible next states to S0. So either the enable pin is true, and then the counter will increment to 1, or the enable pin is false, and the counter will stay at 0. So, but neither of those values are 10, so the property cannot be violated. We can also like extend this, so we can make another state S2, and then we can say, okay, starting at S0, then S0 is followed by S1, S1 is followed by S2, and then we check, can the property be violated in S2? And that would be like another step, and you see like the formula keeps on growing that we give to the SMT solver, but basically it keeps on being unset. And now we could extend this like manually forever, but basically we're like programmers here, right? So we want to write our own program. So this is an implementation of this BMC bounded model checking algorithm. So what we do is we say, okay, we make the initial state, and we have this condition that the initial state, this state 0 is the initial state. And then we just iterate from 0 to k. And what we do is we say, okay, we solve all the conditions that we have, plus checking whether the last state, the previous state, can have an error. And if that's true, then we'll actually print out found a bug, and we'll like sort of print out the example. If it's not true, then we'll continue. We'll make another state. Basically, if first we had S0, then we'll make an S1, and an S2, S3, S4, S5, and so on. And then we'll just add to the condition that it is this state succeeds the previous state, and then we'll set this state to be the previous state. So basically, we're just building up this formula the way we're doing it here. We're just doing it with a loop instead of manually like copying things around. So you make another state, and then you say, okay, this state is now the state succeeds the previous state, and then we check this state in the next iteration of the loop. So we can try out our implementation here. And for now, we just do like a check for like 5 states, right? And it won't return anything because there's no error. But what we know is that if we increase it to 10, then it will actually find an error. And we see here, it will actually like show us how to get there. We'll say, okay, this enable has to be like 1 for these steps. And then the counter will always increment. It will go from 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9, then to 10. And then the property is violated, right? So, so this is like a way that you can find property violations. And if you like simplify the system enough, then it's actually kind of easy to implement this. One thing that of course we don't do is we still, in this like simple implementation, we have to actually implement our like transition function and our initial state function manually. Whereas like if you use the Chisel verify function here, then it will all be done automatically. Like it will compile your circuit to Fertile, and then it will convert the Fertile into this representation internally, and then it will build up the formula for you. But if you just want to do it for one circuit, it is actually like not too hard to implement this on your own. And I encourage you to like play around with this a little bit after the lecture. So now let's just like visualize a little bit what's going on here with the bounded model checking. So basically, this is like a state space visualization. What we mean by that is we just like put this rectangle here. We say, okay, this rectangle is the space of all counter values, right? So the counter has 32 bits. So it could be any value between 0 and 2 to the 32. And basically, we know the starting state is counter is equal to 0. And we know the error state is counter is equal to, okay, in this case, like I had 500, we had 10 earlier, but let's say it's 500. And so now if we do BMC, what we basically do is like every step, we basically increase the area or the state space in which this counter could be in, right? So like basically in step 2, it could be either 0, 1, or 2. In the previous step, it was just 0 and 1, and in the first step was just 0. So we basically just increase the space, and we're kind of trying to search to see if there's any way that we can get to this error state. And the problem here is, of course, like how many steps do you have to check to be sure that you cannot get there? And the answer is that there's not really a lot of certainty. Sometimes for some designs, you kind of know, oh, this is the depth, so this is kind of how many steps I should do. Most of the time, what actually happens is that the more steps you do of this BMC, the slower it gets. We talked about the fact that this SAT solving or this SMT solving is NP hard. So that means at any possible point in time, it could suddenly get really, really slow. So basically what you do in practice a lot of times is you just increase the size of your BMC, like the number of steps. And at some point it just gets so slow that you just give up. That's kind of what happens in practice. So now, okay, now we're done with like looking at like BMC sort of from just like the algorithm perspective. Does anyone have any questions right now? All right, then we'll continue. So for now, I promised you some applications. And so the application we're going to do is we're going to verify a queue that you're familiar with. It's queue number 6 from the queue lecture. And for queues, I guess I already told you with the whole like Graycode verification. One of the hardest parts, basically, or one of the things that like is important for formal verification is that you find a nice property that you can check. And so a lot of times, I think these properties are kind of hard to figure out. And sometimes it just comes from experience or from like looking at other people's code that you know some properties that are neat to specify. And I want to like show you now like a queue property that is cool to specify that I just learned by looking at someone else's code. And so this property is basically like data integrity property, which means that if something goes into the queue, it should come out again. And it should be the same value, right? Because the queue shouldn't change the values inside. And it should come out after the right number of other elements come out. So if you like put something in the queue and 2 elements are already in the queue, then after those 2 elements come out, then you expect that 1 element to come out. So that's sort of the basic idea here. First of all, though, I want to like actually like just add a little trace component here to our queues. So this is a general setup that we do for formal verification. We'll just instantiate the queue. So here we say 3 entries, bit width 8. So it like always pays off if you have a generator to like verify a smaller instance of it, especially like not so many entries, because then you can have pretty high confidence even with not so many steps in your BMC. And what we do here is we just make an IO that's just the same IO as the queue has, and we just like connect the queue to that IO. So basically we're just making a wrapper to the queue that just like puts all the signals through to the top. And then what we do is we'll actually observe when things enter and exit the queue, and we'll count how many things are in the queue. Because as I said earlier, like it's kind of important to know how many things are in the queue so that you know when to expect the element to exit the queue again. So here we're just making a counter that starts at 0. And basically we like add 1 if we enqueue something, and we subtract 1 if we dequeue something. And so this kind of works here because fire is a Boolean, but a Boolean is also a 1-bit uint. So basically, if fire is true, we'll add 1. If it's false, we'll add 0. If here fire is 1, it will subtract 1. If it's 0, if it's false, we'll subtract 0. And then this is our next element count. And then we just add some tracing here just to see like what's going on. We'll print out what cycle we're in. We'll print how the count changes. And if something is enqueued, we'll say here, oh, maybe let's say like, oh yeah, enqueued. Or if something is dequeued, we'll say, okay, this is dequeued. And of course, now if we execute this, it won't actually show us anything because the queue is only actually executed if we find a bug, right? So only if something fails will it replay this failure. Otherwise, we'll just try to like completely like basically prove that it's correct. And since there's no assertion here, it's very easy for it to prove that it's correct because it basically says there's no assertion, so it's always correct. So we'll just add a fake assertion. So I have this helper function here, which will just add a counter, and it will just basically make your circuit fail after 3 cycles in this case. And that's just nice because it will give us a visualization of what the queue can do. So here we see there's a 0 that's enqueued, there's another 0 that's enqueued, another 0 is enqueued. And so the count goes from 0 to 0 because nothing happens in this cycle. Then it goes from 0 to 1, from 1 to 2, and from 2 to 3. So that's just like showing you how this trace stuff works. And this trace stuff is just going to be important later for us to debug either the queue or our verification component. So now let's get to the property. So this is like a naive version of this. So we're going to build up a little bit, like from like simpler versions to like more complicated versions. So here we're basically just saying, okay, there's a state which is active. So is active basically indicates, are we tracking a packet right now, or are we not tracking a packet? And in the beginning, we're not tracking a packet. And then we have a packet value register that will just be able to help us to save the value of the packet. And so what we do here is we say, okay, when we're not active and there is a new packet in queued, then we'll say, okay, we're active now, and we'll track the packet value. And then whenever we're active and a packet is dequeued, we'll check that the value is actually the one that we expect, and we'll become inactive. So this should work, right? Because like the first packet that goes into the queue will be not active, so we'll track that packet. And then, of course, because it's the first packet, we also expect it to be the first to come out at the end. And so now we can execute this, and it should just work, hopefully. But oh no, it doesn't actually work. So what is going on here? Well, we see that we're tracking. So there's 16 enters the queue, and we're tracking it, and the number of elements is 0 right now. And then in this cycle, the solver says, okay, let's put 32 into the queue, and let's get 16 out of the queue. And we're saying, okay, that's great. Like here, we're saying, okay, we got 16 out, and we were expecting 16. But now what happens is we enter 0 into the queue. And remember, there's already the 32 is in the queue also. And now we're entering 0 into the queue, and now we're saying like the next thing that's dequeued, right, is 32. And now we're saying like, oh, 32 is not 0. That's bad. But that's actually like our problem, right? Because like we don't actually expect 0 to come out just yet, because there's a 32 in it before it in the queue. So basically, you think about the queue, right? We're putting 16 into the queue in the one cycle, and then in the next cycle, 16 gets put out of the queue, and we put 32 in, and then we're actually putting 0 in. And basically now we're saying, okay, which we're tracking 0, we're saying, oh, the next element should be 0. But the next element that comes out of the queue is actually 32, right? And then only in the cycle after will 0 come out of the queue. And so basically what that means is we have to do some counting that we're not doing correctly. So that's the next iteration of this. We'll actually add a packet count. So here, this is all the same. This is active is the same, packet value is the same, but now we have this new register called packet count. And what do we do with the packet count? Well, the one line we have to add here, we have to say, okay, the packet count is just the next element count. So we're just like basically checking how many elements are in the queue when the element is put into the queue. And then when we're active and something is taken out of the queue, we just decrement the packet count, but we only get active if the packet count goes down to 1. Only if the packet count goes up to 1, that means that this is our packet. So because that was the problem earlier, right? The problem earlier here was that we would track this 0 even though there was already a 32 in there, and then the next thing that came out, we're like, oh, it's not 0. But we should have actually just waited one more cycle because this 32 was already in the queue when we started tracking 0. And so this is what we're doing here. We're basically just we're keeping count of like how many elements were in the queue when we started tracking the packet. And then we'll only check the packet if we know that enough other elements were taken out of the queue that we should now expect the packet. So now we can run this and see what happens. And now we see, oh, there's another failure. So what's going on now? Is it us or is it the queue? So here we're seeing, oh, we're tracking 0. And then we're checking 0, and that's all great. And the count goes from 0 to 1, from 1 to 0. But now there's something really weird happening here. The count of elements goes from 0 to 3. Like that should not be possible, right? Like you shouldn't just be able in a single cycle to enter three things into the queue. And we also see that it's not actually like entering something, it's removing something from the queue. So we see here, it's putting something into the queue, it's taking it out. So that's great. That's like how we expect things to go. But then it's taking out another element, even though the queue is empty. And so that's kind of a problem, right? Like you shouldn't be able to take something out of the queue when the queue is empty. So so that's like sort of like how you can look at this trace. And I have to say, like it took me a lot longer to analyze this trace when I saw it the first time. So don't feel bad if you don't see it immediately. But basically the explanation here is that, oh, we're looking at putting something in, taking something out, and then taking another thing out, and that should not be possible. So now our suspicion is that there's actually something wrong with the queue. And so we go back to the queue, and we see, oh, how is this dequeue valid defined? So it says, oh, dequeue is valid when it's not empty, but the queue should actually be empty. So something is wrong with this empty signal. And so here the empty signal is defined as like indices equal and like not maybe full. And so something is fishy with this. And so to be honest, like what I did to debug this is I actually like looked at another implementation of the queue and looked at how the maybe full signal is assigned there. And it turns out it was actually done a little differently. So it was done like this and not like this. So this is sort of the original here from the lecture. And so this is what I found some other implementation was doing. And so we can switch between this. So by saying this is true. So now we basically change the implementation of the queue to like you assign the maybe full signal in a different way. And so now we kind of have to reevaluate a couple of things. Okay. And now we can like try our checker and see if it finds another thing. It'll take a little bit of time because we're actually like, this is like actually the longer check that we're doing here. So if you look at it, oh, and it comes back and there's no error. So it looks like maybe our queue is actually correct. If you think about like how to choose this bound here, and we know that the queue has up to 3 elements, so we should at least make it like 6 or 7 because we want to give the solver the opportunity to make the queue all the way full and then get all the elements back out. So for queues, you normally want to do at least 2 or 3 times the number of elements inside the queue to be sort of have some certainty that the queue is correct, which is why it's nice to like instantiate the queue with a small number of elements to check it. So the one thing that was kind of missing from the previous example, but it actually doesn't lead us to new bugs to add this. But I kind of want to show it here for completeness sake is that, well, previously we were sort of like picking the element that we wanted to track just by saying like, oh, whatever the next thing is that gets enqueued after we're not active is the one that we'll track. But now we'll basically just give the solver a little more freedom to decide which packet to track. And we can do that by giving it this enable pin. So basically this enable pin is like completely like chosen by the solver. And basically the guarantee that you get from the solver is it will always try to find the worst possible input, right? And so here we're allowing it to like say, oh, don't track this current packet, track like the next packet, right? So if it sets enable to 0, then we'll just ignore a packet and we'll track the next one. And so this will allow the solver to basically track any possible packet. And so this is then basically the full version almost of this packet tracker. There's like some more complicated things that that you can add if there's like other things that your queue supports. But this is sort of a pretty complete version of how you can express this data integrity property. I encourage you to play around with this a little bit at home. This is actually like a pretty universal like idea that you can actually also use for other decoupled components that might even have some transformation on the data. But yeah, I thought this is like a cool example. And as I said, like this is not something you will come up with on your own, but once you understand the pattern, I think this will help you understand a lot of other formal verification patterns. So yeah, just to summarize, formal verification can exhaustively verify a circuit. For combinatorial circuits, it always does that. For circuits that have registers, we have to choose a bound. And basically with the method that I showed you, which is called bounded model checking, you never know if that bound is sufficient. You basically just increase it and with it increases your confidence, but it's really hard to prove that your bound is so high that there can never be a problem unless you have like a very trivial circuit. The one important difference between formal verification and the testing that you've done is that the checker needs to be written in Chisel. So it's not just a software checker. And the nice thing is that the checker can actually be pretty small if you find a good property to check. So this queue checker that I showed you, I have like a slightly extended version of it, and it can check any queue basically that you throw at it. And it's kind of shorter than like exhaustive unit tests for the queue would be. But it's hard to find the right property to check. So that's like the problem here. We can find interesting corner case bugs, as you've seen with the queue. I have links here to some more examples if you want to look at them. You can feel free to email me if you have any questions about any of this, or if you want to like discuss any of this after the fact. There's a link to the Chisel test library. And there's also like a Chisel community chat if you have any questions about Chisel in the future. Yeah, so I have some bonus slides which we could get to if we want to, but first I want to like make sure that if anyone has a question about any of the material today, that they have time to ask it.
Great talk so far. I've been watching the chat. I think so far it's been commentary rather than questions. So
cool.
We'll give another minute for students to speak up any questions. Otherwise, we'd love to see those bonus slides.
Are these slides, Professor Beamer, are you going to make these available in on the course website?
I would love to. Hopefully I can work out a way with Kevin to get these in the pull request or something.
Yeah, I think they're already in the pull request. So
oh, great. Oh, well, then I should check my email then. Thank you. And then from chat, there's a question from a student asking, what's the largest design you've ever formally verified?
So I guess like one thing you have to say is that like the slowness of the verification doesn't necessarily depend on how big the design is. There is some correlation, but it also depends on what property you're checking. So the largest thing that I've ran is like, well, there's like one thing where we basically have like a processor that has some security assertion, and we're trying to find like some instructions that will trigger the security assertion. So I've been able to run that, and that was like very, very quick actually, because it just had to generate a single instruction basically. So that just took like 10 seconds to run. So this is like a processor without like a huge like memory system and like not an out of order processor. Besides that, I recently had a part of Rocket Ship that I ran formal verification on. So basically we have the like two L1 data caches that are like non-blocking, and we have like a simple like coherence fabric and a simulated RAM. And I kind of ran a check on that, and it like hit some assertion violation. But at that scale, the Chisel built-in support is still a little struggling. So I definitely think for beginners, it makes a lot more sense to like try to verify smaller things like a queue or like a simple function. Okay, if there are no more other questions, I'll just use the last like 6 minutes to like go a little bit over the bonus slides. And also feel free to like study them a little bit on your own. So basically there are two things that I wanted to like show a little bit. So one is like temporal assertions. So right now our assertions were all sort of on like a signal that should have a certain value in a single cycle. But a lot of times, especially if we talk about like bus specifications, like for example, the AXI4 specification, there are properties that actually span multiple cycles. And so here we see that there's this restriction. So AXI uses ready valid protocols that like what you're familiar with your queue, but it has like a certain restriction where it says, okay, if you assert valid and ready is not true, then you have to keep valid true in the next cycle until ready becomes true. And you also have to keep that information, the bits, you have to keep them stable. And so here's a very small example of how we can like show this property or check this property. And it's using this special function here, which we defined in Chisel test. Is called the past function. A past function basically just says like, look at the value in the cycle before. So here it's saying like, oh, if in the past valid was true, but ready was false. So this is basically describing this situation here. Valid is true, ready is false. Then make sure that right now valid is still true. Because if you like suddenly like revoke valid to 0, then like then you're like violating this AXI specification. We're also saying that the bits should be stable. Stable means that the current value of the bits is the same as the value in the previous cycle. So that's also a temporal assertion. So this is a very simple way here in Chisel test that you can write these temporal assertions. The nice thing is they also work in simulation. So if you write a test bench here, so here we have a simple test bench, and you're probably going to want to step through the details on your own a little bit. But basically here we have a test bench where we like make a transaction happen, we like change things, but then the transaction stops. And now if we change something, if we change the valid back, then it says, oh, valid may not be deasserted. If we change the bits without a transaction happening, then it will tell us that the bits changed. Yeah, here it says, oh, the bits changed from 234 to 123, and that's not allowed. So this is like a way that you can like specify things that take multiple cycles, and it works works for a test, but it will also work for formal verification, of course. And this is like all sort of like in the industry standard languages like System Verilog or VHDL. There is support for even more complicated temporal assertions. So if you're interested in this, there's like PSL, which is like the VHDL version. There's System Verilog assertions, which is System Verilog version. You can like look at these examples on your own time. Now, this is also going to be probably a little fast because we only have 4 minutes left, but I just wanted to give you sort of an idea that there are ways to exhaustively prove that something bad can never happen on a circuit, because we've seen with this BMC, you can find bugs, but if you increase the threshold, you still don't know if you actually like exhaustively check the circuit. So now we're going back to the counter example, this my counter thing that I want to prove correct by induction. And we know sort of now the bad state that we're trying to say is like, so it's bad if the property that we want to hold is that the counter is never equal to 500. And you know, if you think back to it, the counter only counts up to 22 and then it goes back to 0. So this should never happen, right? But how many steps would we need in BMC to exhaustively prove that? That's kind of hard to figure that out. So going back to bottom model checking, right? So bottom model checking starts at a starting state and it sort of like extends from there. It will sort of increasingly search this possible space of counter values, and we'll see like which ones are actually reachable. But the question is, like, can it ever get here? And we can't really like prove that it will never get there. But there's another way that we can actually prove it, and it's called induction. So induction basically just says, okay, we checked it in the base case at the starting state. The property holds. So we say, okay, when the counter is 0, then we know that the counter is not equal to 500. Okay, so this is basically just like our BMC check for the first cycle. But then we say, okay, now assuming that we are in a state where the property holds, and there is a next state, then the property will hold in the next state. And so basically what we're saying is like, okay, starting anywhere. So basically the state where the property holds is basically every part of this rectangle besides that red dot. So every part of here, we're saying like, okay, you can start anywhere. And if you go take a step, then you won't get into the red circle. But the problem is this will actually happen, right? Because like we can say, okay, the counter is 499, which fulfills our sort of restriction that the property holds. So for the counter is 499, the property holds. And then from 499, we can go to 500. And so it says like, oh, this property could fail. Of course, it cannot actually fail because you also cannot get to 499 from here, right? We know that we can only get to 22. So what we can do is we can add a strengthening invariant, which basically says, okay, we restrict the space to values that are where the counter is between 0 and 22. And you know, that space is mutually exclusive of the counter being 500. So if you can prove that the circuit will always stay within this space, then we can actually prove that this property always holds. And so that's exactly what we do. We basically say, like, okay, given any like point in this circle, if we take a step of our system, we'll always stay within the circle. And we know that that's true because if the counter is like any value between 0 and 22, we know that the next value will either be +1 or it will be 0 if it is 22. So we'll always stay within the circle where the counter is within that range. And so now we can actually like run this again with our system, similar to how we did the BMC. So basically, we'll just we'll check the induction step without the strengthening. So we're saying, okay, the property holds on S0. There S1 follows S0, and then check is it possible that the property won't hold in the next state. And if we execute this, it will actually show us yes. If the counter is 499 and then you take a step, then the counter will actually be 500 and you're screwed. But we know that this is a false counterexample. So we call this like a spurious counterexample because it cannot actually occur in the real world. Now, if we add the strengthening invariant, we basically just say, okay, 22 is always greater or equal to the counter. And so we just like make a combined assertion. We just say, okay, the initial assertion plus this new one. And now we can do the induction step again with the new combined property. And if we do that, we'll actually get unsat, which means that it's proven that for any possible, that no matter how long you execute your counter, it can never be 500. And so this is something you can do with induction. This is a one induction because we only took one induction step. K induction means you can take multiple steps, but that goes a little beyond what we want to discuss for this lecture. So yeah, thank you very much for listening. I know the bonus slides were very fast. They're not super important, but if you're curious, try to like work through them yourself a little bit. And yeah, thank you so much for having me here.
Thank you. That was a tremendous talk. I really enjoyed it. I thought the verification assertions for the Graycode was really neat. I have a couple of questions in mind. Maybe I'll be quiet first if students or anyone else has questions first.
Oh, hi, Kevin. I have a question. So whenever possible, is formal verifications preferred over traditional tests?
I think that depends on a lot of factors. It used to be for a long time that like formal verification, there wasn't a good open source way to use it. So basically, like we used to have like open source simulators for Verilog starting in like the early 2000s, but the first like open source formal verification tool that actually worked with like Verilog was only released in like 2016, and like Chisel only got like support now in 2021, basically. And so for a long time, basically, you could only use it if you were in industry. Now I think it's getting more and more easy. And so, like now it might make more sense because you don't need to buy an expensive industry tool, right? The other thing, though, to also consider is that formal verification is nice if it works, but it doesn't always work. So if you have like a large circuit, it might be really hard to actually write the correct properties that you're interested in. And then sometimes your solver might like stop working because, the base problem is actually really hard. So there could always be a case where your solver just gives up, basically. And then a big problem is also just the training. So like in industry, there's very few people who actually know how to do formal verification. And I think one of the problems here is that because for a long time, you couldn't actually play around with it on your own. You could only play around with it if you buy the expensive industry tool. But now I hope that with this being integrated with Chisel and like being fairly easy to set up, that more people can play around with it. And so, if you actually do have the necessary experience with it, I think it is a very powerful tool that can sometimes replace testing, sometimes just augment testing. So for example, for our Q example, there's actually one thing I didn't talk about, which is you can actually like trick the checker by just making a queue that just never accepts any value, because we're not actually checking whether it accepts any values. We just say if it accepts a value, then it has to come out uncorrupted. So if you have a queue that just never accepts any value or never lets you dequeue anything, the property still holds. So in that case, like some testing that to make sure that you can actually put something into the queue or make it all the way full is very advisable.
Yeah, I see. Thank you so much.
Yeah.
So the temporal assertion was really interesting. I think that kind of gets at a broader question I have, or it seems like sometimes when we're trying to test, we have a notion of functionally what we want to do. What the circuit's supposed to do, but part of the complexity, the circuit is actually, trying to do that over multiple cycles or whatever. So perhaps via the coupler, perhaps via other mechanisms, you can imagine some circuits might, take multiple cycles to produce the correct answer. So is there kind of a way to do like a path to an arbitrary cycle number, or how do you recommend doing a situation like that?
Well, if you have like a decoupled interface on the thing, then it's kind of similar to a queue, just that the queue like transforms the data. So you could just use the queue checker and just say that instead of like checking that the data is equivalent when it comes out, you just check that the data is equivalent to the transformed data. So that would be like one way to phrase it.
Great. Yeah, I mean, it seems like part of the art of this is figuring out those assertions, right? And so, cool. I mean, this is definitely a fun new world. I'm excited for us to play around with this. Hopefully, students will be able to use this in their project in the coming few weeks. Any last questions? Okay, well, thanks, speaker, once again. That was a great talk.
Thank you. Thank you for having me.
Thank you again for helping make this Chisel course, right? We've had students learning Chisel, one of our good people from the Chisel community coming to share what they've learned. It's really a nice thing to do. Thank you.
Thank you.